We've got some new identities today. We're starting 5.4, multiple angle identities. Today we're just going to focus on the double angles. And this is something where we look at the relationship of not just, for instance, the sine of a 10-degree angle, but that double that angle. So the relationship between that and a 20-degree angle. And we're going to mostly look at just relationships. We'll do a little bit with actual values so you kind of understand the process, but typically double angles are used more in a theoretical fashion, recognizing relationships between angles. In this box here, you'll see all of the double angles. You do need to know the double angles. In order to use them, you've got to recognize when they're happening. The double angles actually come straight from the sum and difference identities. I'm not going to prove all of these to you, but just so you recognize a little bit of, this isn't magic, this is just math here, where this came from. If you think of doing the sum and difference identity of, let's do a sine. So let's say sine of two angles, and I'm going to just make it be like two angles that happen to be the same. For instance, theta plus another angle, I'm going to call it theta also. If you use your sum and difference identity for sine, remember that goes sine of the first angle, cosine of the second angle, plus sine of the second angle, cosine of the first angle. Well, that's all the same thing. That's sine theta, cosine theta, added to itself. Again, you can see why we would come up with this when you take 2 times theta, because 2 times theta is the same as theta plus theta. These are equivalent expressions, so you can see where this would lead to that. And we could continue to do that with all of them. On cosine, we actually have some options. This is the normal one that we would typically use. But as soon as you have some squared functions in there, you start thinking Pythagorean identities. And if you were to replace cosine squared with 1 minus sine squared, you'd end up with 1, well here I'll just write it up here, 1 minus sine squared theta, and then minus sine squared theta, which would lead us to this right here. This is the normal one that we use. These are the two that can be derived using a Pythagorean identity. Here I replaced cosine squared to get this one. If I were to replace this with 1 minus cosine, I would get this one. Each of them has their own specialty when they would be used. What's nice about these second two is they only have one trig function in them. So if I'm working with something that has a bunch of cosines, I'd rather use this one than the other two. And likewise, I'd rather use this if I was trying to deal with sines. Tangent can just be derived by taking your sine over your cosine. All right, so that's it in a nutshell. Basically, we're just going to practice using these double angle identities today. Keep this page in your notes handy. We'll be looking back at those. I like to start off and do with some actual angle measurements so you understand really what this means to use these identities. If you look at this first one here, I have the cosine squared of a pi over 3. Remember that when the squared goes here, it means you find the cosine of pi over 3 and then you square it. Sine squared pi over 3. Notice that you're subtracting. Now I'm not really going to go to my unit circle right now and evaluate that. Really what I want you to recognize is, oh, this is really an identity. This is the cosine of a double angle. It's the cosine of 2 theta, but not really 2 theta, it's 2 times pi over 3, because that is my theta. And if you think about what 2 times pi over 3 is, well, that's just 2 pi over 3. Cosine of 2 pi over 3. When they ask me to evaluate this, I'm not going to worry about having to try to figure out what the cosine of pi over 3 is and then squaring it and then doing it over here and then subtracting. I'm going to look at this and say, oh, that's just a double angle identity. I really just need to find the cosine of 2 pi over 3, and that's what it will be equal to. The cosine of 2 pi over 3, I was stalling there, did you remember? -1/2. And that's what you evaluate it to. If you look at B, Ideally, you look at that and say, oh, that's that double angle identity for sine. So this is sine of not 2 theta, but 2 times 90. Well, 2 times 90 is just 180. What is the sine of 180? 0. Okay, so that's evaluating. Now, let's look at the next thing. Let's do some solving using these double angles. You'll have some sort of an expression where you'll have a double angle tucked inside there. Sine of twice the angle x. Now this one's fine and normal, but this one I need to replace. You'll always want to get rid of that double angle. So I'm going to sneak in there. I'm going to go ahead and write my 2 cosine x plus, and I'm going to replace that double angle with my identity 2 sine x cosine x. And then we treat it like we have previously. Looking at that, I think I'm going to pull out a GCF. 2 cosine x. And then I would have a 1 plus sine x left. Set those each equal to 0. I'll end up with a cosine x equals 0. After I divide by the 2, it doesn't matter. And I'm going to have a sine x equals -1 when I subtract that 1 over to the other side. Remember, you're just setting those each equal to 0 and isolating the trig variable, or the trig function. Now, to actually solve it, and we're doing it from 0 to 2 pi, so I'm going to list the exact values out. When is cosine 0? That happens at pi over 2 and 3 pi over 2. Should have x equals on that. When is sine -1? That happens to occur at 3 pi over 2. I already have that listed. There's no need to rewrite it. I'm just going to go with it. This is my final answer here. One more solving. Again, I threw a double angle in there. I threw parentheses around the 2x. Over here I didn't have that. There's no difference, just a different way to see it. Probably needed to do that because it was tucked in with something right after it. I'm going to replace the double angle with my identity. But that's just getting multiplied by another sine x. I think I'm going to want to subtract that cosine x over to the left side and set it equal to 0. And I look at that and I try to decide what to do with it. I think it's another factoring situation. In this whole mess of stuff right here, there's a cosine x, and there's a cosine x over there. Let's factor that cosine x out. In parentheses, I would have left a bunch of stuff here on the left. I have a 2, a sine x, and another sine x. That's 2 sine squared x minus 1. Now you're solving. Let's set each of those equal to 0. Cosine x equals 0. On this one, I'm going to add the 1 and divide by the 2. Sine squared x will end up equaling 1/2, but I have to square root that. Sine x will end up being a plus or minus, and hopefully you've done it enough that you remember the square root of 1/2 is the square root of 2 over 2. Now let's solve. When is cosine 0? Well, it happens at pi over 2 and 3 pi over 2. And then I got to go over here to the sine x equaling a positive or a negative root 2 over 2. That's going to happen at all my 45s. It's going to happen 4 times because of the plus or minus on there. I'm going to have a pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Lots of solutions on this one. Let's try doing verifying. That's something else we've done with the trig identities. We've done verifying. Now let's throw in a double angle into the mix and see how we would do that. Well, sine of 2 theta, just going to replace it. 2 sine theta cosine theta equals And then I got to look over here and decide what I want to do with this. I'm going to leave it as a fraction for right now, but I want you to recognize this right here as a Pythagorean identity. That's cosecant squared theta. Thinking that I'm trying to verify, it would be nice to have both sides have the same trig functions in them. I'm going to take the right side over here and turn this into sines and cosines. The first step, the easier step, is probably to take this and bump it to the top and call it a sine squared. We can put that sine squared on the front or the back end. It doesn't really matter. I'll go ahead and leave it on the back end there. So I'm going to have a 2 cotangent theta. I'm going to go ahead and change that cotangent while I'm at it to a cosine theta over sine theta. And then I'm going to bring that cosecant squared up and call it a sine squared. But since it's in the numerator, if you want to put it over 1, that maybe helps you. If you look at what happens here, you have a 2, and let's look at what happens here with our fractions. This would reduce with that squared, and all you have left is cosine theta, sine theta, and looky there, we just verified that was an identity. Sometimes we're going to get some problem that has something kind of funky looking like 4a or 8a or 6a or something else in here, meaning that the angle is not just the regular angle, but it's 4 times that angle. Now, it's kind of like a double angle. It's a double of a double angle. What I want you to recognize is that you can do some replacing of this. If you see this particular situation right here, you should look at that and say, hey, cosine squared minus sine squared, that's a double angle for cosine. In your mind, you're thinking cosine of 2 theta is equal to cosine squared theta minus sine squared theta. That's the identity right there. Now let's look at how that compares to this one up here. If I've got the cosine squared of theta, so right now theta is 4a, minus sine squared theta, which is 4a. If theta is 4a, what would 2 theta end up being? Well, it'd be 8a. This whole thing right here could really be reduced down to a single trig function, cosine of 8a. And you might need to do that as you're simplifying problems or verifying. You might need to be able to combine those and see something, how that would end up being an 8a. Look for that to happen. Last type of problem that we might have is something that doesn't necessarily always fall perfectly on the unit circle. And how do we deal with those types of problems? Let's find the exact value of each given that, of each of these is what that means, of each, given that the sine of u is negative 4/5 and you know u is going to fall between pi and 3 pi over 2. Hopefully you look at this and think, oh, that's that one where we have to draw triangles on because it's not straight off the unit circle. This right here is just telling you where to draw the triangle. Between pi and 3 pi over 2 means it's going to fall in the third quadrant. Let's draw our triangle in the third quadrant then. U is your angle. It's always up here by the x-axis. And sine is opposite over hypotenuse. Now when you look at that, notice that the sine was negative. You got to put the negative on the 4 or the 5. The hypotenuse is always positive, and this would make sense since it's going down. The 4 should be negative. And then you can do a Pythagorean theorem to find the missing side. Maybe you know that's a Pythagorean triple. This is going to have to be a 3. But notice also, since you're going left, you need to acknowledge it would be a negative 3. Knowing that, we can find any trig function that we need. For A, this first example, it's not just find the sine of u, it's find the sine of 2u. I'm going to need to use my identity for that. The sine of 2u is equal to 2 sine u cosine u. That's your identity. 2 times. Now I can figure out the sine of u. In fact, the sine of u was given to me as a negative 4/5. Times the cosine of u, I can use my triangle. Cosine is adjacent over hypotenuse. And then if you want to think of your 2 as 2 over 1, and you're just going to multiply these straight across, you end up with a 24 over 25 for the sine of 2u. Let's try another one. Let's do cosine of 2u. You can use any of the 3 identities that you want. We've used the cosine squared minus sine squared several times. Let's try one of the others. Let's do the 1 minus 2 sine squared u. Let's try that one. You're just going to take 1 minus 2 times, and the sine of u they actually gave us, negative 4/5, but I'm going to have to square that value, and then we'll simplify. 1 minus 2 over 1 times, if I square this, I get 16 over 25. I'm going to end up needing a common denominator, so I'm going to go ahead and write my 1 as 25 over 25 minus 32 over 25. My final answer, negative 7 over 25. And I should have gotten that regardless of which of the cosine identities I used. All right, we haven't practiced with our tangent identity. Let's try that. Looking back at your identity, you need to, in fact, that one I might write for us. And then we have to start plugging in values for that. In my numerator, I'll have a 2. Think of it as a 2 over 1 because the tangent is going to end up being a fraction. Tangent is opposite over adjacent. That's going to be your numerator. Over, the denominator is going to be 1 minus that tangent value of negative 4 over negative 3 squared. Just working with some fractions here. In your numerator, you're going to end up with a negative 8 over a negative 3. I'm sorry, I'm going against the rules. I'm going to go horizontal here. Negative 8 over negative 3 over, on the bottom, I'm going to end up with a 1 minus 16 ninths. So I'm going to call this 9 ninths. And just to show it to you here, 9 ninths minus, sorry, this is a really messy pen, 16 ninths would end up getting you a negative 7 ninths. That would be your denominator, negative 7 ninths. But we don't divide by fractions. We'll end up bringing that up and multiplying by the reciprocal. This 8/3 is actually going to end up positive because you got 2 negatives, but the 9/7 is negative. When I multiply here, I'm going to end up with a negative. I'm going to go ahead and reduce the 3 and the 9 and do that with a different color. So that's going to be a 1, and that'll end up being a negative 3. When I multiply straight across then, my final answer will be a negative 24 over 7. Final answer. Okay, there's a lot of uses for these identities, and really we're just tying it in with the verifying, the simplifying, the solving, all the stuff that we've already done, just throwing some new identities, making you practice those algebraic steps that happen, but this time they're with trig functions. You do need to know your double angle identities. Study those.